Hello, welcome back to Engineers Ireland. Today I want to cover two small topics. They're extremely important because they lead into several chapters. Now I want you also to recognise one other thing. We've really just dealt with the regular geometry and algebra chapters up to this. The concepts in those chapters were really introduced to you for your junior cert. And probably because of that, a lot of people feel more comfortable working with those chapters than they do with ones that now come in and are new to them for the Leaving Cert. And one of them is the section I want to start with, which is difference equations. Okay? Now, they're also called recurrence relationships. They come in towards the end of the chapter on statistics, but really they belong with two or three other chapters. If you understand these, it makes it easier to understand series and sequences. If you understand those, then the special question, the question 8, which is in part 2 of paper 2, becomes very easy. Because remember, that question 8 is not further calculus. It's further calculus and series. So, what are these relationships? Now, as I've mentioned to you, I am using one of the standard textbooks. It's Aidan Rowntree book. And he starts this on page 168. Fundamentally, when you just start looking at this, you're also getting a very easy introduction to what a series is, and sequences are very similar to it. If we had you'd be wondering what comes next. Now, if you look at the difference between these, you find that there's 4 between each of them, so you could pretty much guess that the next one is going to be 4 bigger. So we'll say you're just guessing that. Now, by the way, what you probably don't know is that that little system of finding differences, and it works not only for nice little linear things like this, it'll work for answers that actually were generated from a quadratic equation, which you may not know the answer to, and under those circumstances you can get the differences of difference and run down. That system was developed by the Arabs about 1,000 years ago. Algebra is the name given to one of the great Arab mathematicians, and we get the term algebra from his name because his book made its way in around Europe, and the Europeans used it quite literally up to the 1800s. So his name is basically what you're using when you say algebra. But anyway, for what we're dealing with now, we're saying there's a common difference between these particular things. Now, what if we had a situation like this, where we're saying each one of these we're going to give it a name, and we'll say that's U1. Tradition has us calling these things U. We can say this one could have the name of U2, U3. Now we could have a situation where we know that U3 is equal to U2 plus 4. Now fundamentally, what we've written there is the rule governing this set of numbers along here. We're saying the next one on, the third one, is equal to the previous one plus 4. Nice and handy. Now very often the relationship just doesn't deal with the previous one, it can deal with 2. In other words, might have to do with the U2 and the U1 there. Now, just before we move off it, based on this we would be able to say U4 is equal to U3 plus 4. And the reason I'm moving on to that is how we get to that one is you can say I can put in the number, any number, And for the general case, what we'll get is this. It's equal to the previous one. Saying my nth one, the one I'm looking at now, that particular term is going to be the one before the n, which is the n minus 1, and 4. It's important just to get this naming concept and this kind of system of being able to talk about something such as the nth term in relation to a 1 before it or even 2 before it. We could have a situation where un is equal to some constant outside of 2 to the power of n plus m outside of 3 to the power of n. A lot more complicated than the last one, but not really. You get used to these things. Now what we're saying is our nth one here, that could be our 5th one, it could be our 7th one, it could be our 9th one, or our millionth one. We're saying it's going to be some number, which we've just called k now, and it gets multiplied by 2 brought to this power of n. So for example, u3 will be equal to k by 2 cubed plus m by 3 cubed. So you can see how that works. We're saying this is my 3rd term in a series from u1, u2, u3, and on and on and on. And its answer is that. Now then, just so that you get exercise in using not just 3s and 4s in here, because they're the easier bit. What you really have to get used to, and I'm saying to you it's important to do a number of the exercises just to get clear on this, is we have been using up here un. If I wanted to know the next one on from this, I'll have to say the un plus 1, that particular one, is going to be, and every place that I have an n up here, I'm going to be putting in an n plus 1. This is a bit like when you're using ordinary functions such as y equal to the function of x, and we will just say that it was x squared plus 3x plus 7. And we're saying when x is 5, we're saying the function at 5, and you just plug in the 5 for the x's. Here what we're doing is we're plugging in n plus 1 every place we've got an n. So now we're saying it's k by 2 to the n plus 1 plus m by 3 to the n plus 1. Now, in the first maths class, I was mentioning to you guys that it's really important to be able to do things like this, and this is the very little problem I gave you. 2 to the 7 minus 2 to the 6. What is that? And the trick was to be able to relate one of the numbers in terms of the other one. Find out whether it's a first cousin or a second cousin. Just find the relationship. 2 to the 7 is 2 by 2 by 2 by 2, etc. for 7 of them. So we can say, isn't that 2 by 2 by 2 by 2 by 2 by 2, etc. for 6 of them? And now we're saying these are the same things. So I can name that to anything. I can call it an apple. So it's 2 apples minus an apple is equal to an apple. Now, haven't seen that. Let's just do the same type of thing with our equation here. This is equal to, it's k by 2 to the n plus 1. Isn't that 2 multiplied by 2 to the n? And a k multiplying into that. So we will say it's 2k by 2 to the n plus, and over here 3 to the power of n plus 1. That's a whole load of 3's multiplied together. I can pull out one of them, and then we'll say there's a whole other 3 to the power of n multiplying into it. So we'll say, now that's basically how you break these things down. And really, once you understand this, going from something like that to this, then you'll have no trouble at all with these recurrence relationships. So far, we're just looking at ways of expressing a term. What we would like to get is a way of expressing a term in relation to the previous terms. Maybe one of them, maybe two of them. Generally for the Leaving Cert, they don't ask you more than 2. Remember, we're calling a term u. So un is the nth term. Un minus 1 is the one ahead of it. Un minus 2 is the one ahead of that. Don't blame me for this one. This is straight out of the book. But basically, the important thing about this is, here's my previous term, whatever answer it was. And I'm saying, if I took 1 away from it, squared it, multiplied it by 4, and took 5 away from that, I'll get the new one, this guy. So I can get the nth one from the n minus 1 one. And that's how it works. Recurrence relationships like these, different equations, they're just basically 2 names for the same thing, are an essential thing for you guys to understand, for you to be able to do a lot of the work in 2 to 3 other chapters. So it's really important to get this as an idea. Now what you'll notice is that I am going very slowly through this. In the last few classes we went really quickly through them. We went quickly through them because they're things that you should know well. The concepts were given to you many years ago. This is a new concept. It isn't hard. It's just not familiar. Okay? And our job now today is to make this familiar. The interesting thing about this particular one is that it'll cause a series, a whole load of numbers as you work out for the different n values. There's only one problem with it. It actually can work for several series. And what I mean by that is, let's look at the U2 one. That's going to be 4 outside of the U1 minus 1 squared minus 5. What's the value of U1? We don't know. If they told us U1 is 1, then we can start a whole sequence from this relationship. If they told us U1 was 270, you get a whole different one, a sequence from that. So there's an infinite number of these things, and it all depends on U1. That's why, to get the specific one, you're given the value of the first one, and we could have been told that this thing was 2. Now I can generate up all of my other numbers. Okay, so then we would say U2 would be equal to 4 outside of 2 minus 1 squared minus 5. And 2 minus 1 is 1. 1 to the power of anything is basically itself by 4 minus 5. So that's minus 1. So we're saying our first 2 numbers are 1 minus 1. Sometimes these relationships don't just have the previous term, they can often have 2 of them. And in those circumstances you're given, for example, the U1 and the U2, or sometimes they'll start naming the sequence as a U0, U1. That's just a naming thing. It doesn't make it different other than how you perceive it. I always prefer starting with U1 because I like to think of 1 as being the first term, but it doesn't have to be that way. And you will notice later on when we deal with series and sequences that how you start off these terms, how you name them can actually make the eventual equations much easier, but you'll get to see that at a later stage. There is a really cute theorem in this section. This theorem is surprisingly powerful. It's easy to prove, and it's one of the proofs that's required, and you could be asked for the Leaving Cert, so it's examinable. What we're basically saying is, what if I have, now listen to this, a second order difference equation. Now a second order one is a one where a term is made up from something to do with two previous terms. Okay? And you'll see why it gets the name second order now in a minute. So we're now saying P we're saying this n plus 2 occurrence, that's the biggest number here, so it's the one that we're really looking at now. We're saying that and the one ahead of it plus the one ahead of it. We have a relationship that has all three of them involved here. Now the interesting thing about that, and this is where the theorem comes in, is I can actually replace this with a second order polynomial, a quadratic equation. So I can actually go P x squared plus this thing here that's the characteristic equation. It's just a name. You can call it Fred for all I care. The important thing is in maths, and I keep saying this to you, when you aren't sure of something, you name it. Fortunately, lots of mathematicians have been doing it for years, so some names are well established. This characteristic equation that belongs to this recurrence relationship up here makes our life very easy, because guess what, if we can actually work out the roots of this particular quadratic equation, and we'll say the roots are a and b, very imaginative naming here, what can we actually say about these? These are the roots of this quadratic now, and you'll notice the quadratic looks somewhat like this recurrence relationship up top, because you've got a p multiplying into something, you have a q multiplying into something, and you have an r. Okay, so what we can find out from this theorem is that if Sn is equal to L by a to the n plus m by b to the n, if we now define our Sn in terms of this, we actually now get back to so then, what is it that we know? We know that if instead of dealing with this unusual equation, that if we turn it into the type of equation that we've been doing and using for years, a simple quadratic, and we solve the quadratic, we will get these roots belonging to the quadratic. Once we've got those two roots, we can say that Sn, this guy up here, which is the first of the three in the sequence, we can now define it in terms of some number L multiplying into a to the power of n plus some number m multiplying into b to the power of n. And that's why the previous example that we were looking at had 2 cubed and, or sorry, 2 to the n and 3 to the n, just so as to get you into the system of thinking in terms of this type of an equation here. The proof to this is actually, it is very straightforward. I don't intend to labour this talk by going through that particular proof. If any of you have any difficulty with this, well, obviously you can ask your teacher, but secondly you can always email us and then I will go through it. But I would think you won't have any difficulty with it. It's in many ways similar to the proof in the factor theorem, which is also examinable. So then, what do we normally do? If we start off with a difference equation, we then appeal to the characteristic equation. We will set up this quadratic equation. We find its two roots. Then we say the Sn is going to be equal to L a to the n plus m b to the m. And we'll say to ourselves, to the n. We'll then say to ourselves, okay, that now will actually allow me solve the big long second order characteristics equation. Let's look at an example, and it's just straight out of the book, okay? Okay, here we have a difference equation. 4 times the un plus 2 term minus 25 times the previous term minus 29 times the term prior to that. We can solve this, but if we want to get a unique solution, we will have to get told what u1 is and u2 is, so that we can start the sequence by doing a u1 here, a u2 here, and that'll then give us a u3, and all the rest can generate away. But we cannot come up with a unique solution without being told what, let's say, u1 and u2 are, or u0 and u1 is. We can still come up with a solution, it just won't be unique. So now here we go, and we will say, okay, for that we're going to go for u 4x squared minus 25x minus 29 equal to 0. I'm reliably informed by the book that this is what we get from that. So now we're saying so we get minus 1 and 7 1/4. One root, the other root. So that's the A1 and that's the B1. Now then, what can we say? We can say that UN is going to be equal to L by minus 1 to the n plus now that's all we need to know, unless we are told what the first two in the sequence are. And we have been told it. We've been told that u0 is equal to 0 and u1 is equal to 16.5. Doing that, we can now work out what the L is and the M is, because we'll finish up with two linear equations which you can solve because they're simultaneous equations. You've been doing those type of things since second year, so it's not a difficulty. The final solution to this, I just want to make room for myself here. So after solving the two simultaneous equations, we find that L is minus 2 and the M is 2. So we just sub it in. I will actually go through and show you a little bit of the second example that's in here, because we actually have surds involved in it, and just in case you think that the answers here always have to be just simple, straightforward numbers, I just want you to see that we have surds on these too. UN plus 2 okay, the characteristic equation has to be x squared minus 2x minus 1 equal to 0, and the solution to that, the two answers are x is going to be 1 plus root 2, or x equals 1 minus root 2. That means so don't be afraid if the answers to the characteristics equation give you surds. It's another number like any ordinary number, and they just get plugged in the exact same way. Obviously, if we're given a value for the start numbers, and in this case we are, we can now go along and we can, that's U0, we can say U0 is equal to the L multiplied by this to the power of n, and the n, don't forget, then will be 0. So what we would get is U0 is going to be L by, and anything to the power of 0 is 1. And anything to the power of 0 is 1. So what we have, it's L plus M, a very simple equation, and U1 will give us, and anything to the power of 1 is itself, sorry, and all we do is we solve. Now, this is only a little bit at the end of a particular chapter, but it's really important that you understand how to manipulate these things and how to play with them. If you learn to do that, several other sections get a lot easier. I would like to just quickly look at one little thing that's at the start of differential calculus, and that's the idea of limits. I don't really propose to cover too much in relation to these, because I intend to devote a lot more time to them later on. I just want to discuss it for the moment. Particularly if we've got a rational expression, something divided by something, and if it's in terms of an x, and it could be, let's say, 1 plus x squared all over 1 minus x. We know we can run into a problem, and the problem is, what happens when x is 1? Because underneath the line we will get 1 minus 1. And that gives us 0, and anything divided by 0 is undefined. So it's really important to be able to know what number the function is running towards. We need to know that because it's at the core of what differential calculus is. You also need to know it because limits are part of the special question. Now, the next class I intend to look at two other small sections that are critical for other sections. One of them is the binomial, which I think most people don't like, but I like it. And the other one is induction. Once we get those two under our belt, and we'll go slowly through those two, much of the rest of the course actually gets easy, because what we've learned is we've learned to manipulate expressions that we're not used to, ones that we would say are not familiar. And once these become familiar, the maths course gets much easier. So that's what we'll deal with the next day. See you then.